Yes, hello, thanks for the introduction. My name is Halley, and I'll be talking about some work that was done jointly with Valentine Kabanets. It'll be giving some connections between witness encryption and the NP-hardness of learning. Okay, so cryptography and learning theory, I think it has long been recognized that these subjects are kind of working against each other. So there's like a sense in which one of these things is possible, only if the other is not. Already in 1984, in his paper introducing pack learning, Valiant already realized that if it could be done efficiently, that would preclude the existence of pseudorandom functions. And these topics have been studied in more depth since then, private key cryptography on one hand, and worst case, average case hardness of learning for efficient algorithms on the other hand. Okay, but that's not exactly what I'll talk about today. So what I'm going to talk about today is kind of versions of these topics that each have more of the structure of NP hardness kind of baked into them. So in the case of witness encryption, I'll be talking, in the case of cryptography, I'll be talking specifically about witness encryption, which is a type of encryption where security is contingent on the ability of an adversary to actually provide a witness, proving membership in an NP language. And then in the case of learning theory, I'll be talking about NP hardness of learning. So does there exist a reduction, say, from satisfiability to a problem about pack learning? All right, so let me give a little bit of background. I won't go into too much depth defining pack learning. I'll just define the type of learning that will be our focus today. So that is called agnostic pack learning. And for this presentation, unless I say otherwise, I'll be talking about learning the concept class of unrestricted poly-size Boolean circuits. So like size S for some polynomial S. One way to model this kind of learning is with a learner being a PPT algorithm that gets oracle access to an example oracle. And each time it queries the oracle, it gets a randomly drawn example that is like a string label pair X comma B from some distribution E. Okay, and then the goal of the learner is to produce a hypothesis H that's like as consistent with those examples as possible. So there's no guarantee here that the examples coming from E correspond to a function, let alone a function computable by a small circuit. So that's why in agnostic learning, we only ask the learner to do as well, almost as well as the best function that does actually belong to size S. So kind of optimal in that respect. And then within this framework, you can also distinguish between what I'll call here proper, semi-proper, and improper settings. So in the proper case, we would require that the hypothesis itself is actually a circuit of size S. You can come up with various sort of semi-proper settings where there's some restriction on the complexity of the hypothesis, maybe not quite so strict as size S. And then there's also the improper setting where there's no restriction on H, just anything that a polytime entity could produce. Okay, and by the way, in the cases of proper and even some semi-proper settings, NP hardness of agnostic learning is known, but it's unknown in the case of improper learning. And that's sort of a big open question that concerns us. Right, so it might not be clear yet what I mean by NP hardness of learning. And in fact, it probably shouldn't be clear yet. So to talk about that, I'm gonna refer to this paper from Applebaum, Barak, and Zhao. They also study NP hardness of learning. And in that paper, they give a couple of definitions of kinds of NP hardness of learning that might hold. So like senses in which learning might be NP hard. So the first one they talk about is called a randomized non-adaptive reduction to agnostic learning over efficiently sampleable distributions. So what is that? Of course, it's a randomized machine R. Let's say it's a reduction from SAT. So it gets a SAT instance phi as input, and then it presumes to have as an oracle an agnostic pack learner. So it makes some queries to the learner, and those queries are in the form of sampling circuits, so poly-size sampling circuits for example distributions E. So samplers for like some string label pairs. And then it expects to get in return from the learner a hypothesis circuit H. And it can look at H and do whatever it wants. And then it's supposed to decide SAT with high probability. One of the results in the paper, they show that if this kind of reduction exists and it works in a sort of strongly improper setting, then yeah, if you're familiar with Impagliazzo's worlds, you can exclude the world called Pessyland. Just means that if you can invert one-way functions, you can decide NP-hard problems on average. So it's kind of a big breakthrough consequence if learning is NP-hard in this way. Okay, now the second type of reduction to learning they define in that paper is much more restricted in the way that it makes use of the learning oracle. So in particular, it only uses the oracle to decide whether a small circuit consistent with the example distribution exists or not. Okay, so really what they're doing is formulating agnostic learning as a decision problem. They call that problem the computational gap learning problem, or CGL for short. Instances of CGL are again those sampling circuits E, sampling examples. And then roughly E is a yes instance of CGL if for some small circuit C is perfectly consistent with the examples from E. And E is a no instance of CGL if for all small circuits, maybe even a little bit bigger, the best the circuit can do over E is probability like half plus epsilon. Okay, they also give some consequences of this type of NP-hardness of learning. That doesn't matter too much for us here. Yeah, so I'm kind of halfway through the preliminaries now, but I also need to talk about cryptography. As I mentioned, there's this thing called witness encryption. This was defined in a paper from Garg et al. In 2013. So a witness encryption scheme consists in a pair of algorithms for encryption and decryption. Encryption is randomized, decryption is deterministic. And the idea is that if I want to encrypt a secret bit B, I do so along with an instance Z of some fixed NP language L. Okay, so I encrypt B using Z, I produce a ciphertext and send it out to everybody. And the guarantee of witness encryption is that if anybody can produce a witness proving that Z is a yes instance of L, then perfectly all the time with the decryption algorithm, they'll be able to recover the bit B. Okay, and then the security guarantee of witness encryption is that if Z is a no instance of L, it doesn't have any witnesses, then encryptions of 0 and 1 will be computationally indistinguishable. And you can distinguish between security against uniform or non-uniform adversaries. Yeah, just for a little bit of context, maybe you haven't heard of witness encryption, but maybe you have heard of indistinguishability obfuscation, which has been studied for a bit longer. Just to note that if you believe in IO, you should also believe in witness encryption. There's a simple construction of witness encryption from IO, and these are both sort of like stronger forms of cryptography that aren't known to be implied by public key encryption. Okay, so this brings us to the first statement we can give. We can show that witness encryption and NP-hardness of CGL are actually just the same thing. So basically this is saying like under some feasible cryptographic assumptions, there is a deterministic polytime algorithm making one query to CGL and deciding SAT, and vice versa. Okay, so a little bit more specifically, we're talking about witness encryption secure against P/Poly, and we need CGL to be NP-hard under a half-Levin reduction. Okay, so what is a half-Levin reduction? Well, I admit that it is a term we define in this work, but a Levin reduction is a very standard thing, and a half-Levin reduction is more or less just half of a Levin reduction. So a half-Levin reduction from L1 to L2 is a pair of machines, R and R sub wit, where R is a deterministic many-one reduction from L1 to L2, and R sub wit is kind of like a witness mapping machine. So it takes an instance and a witness for L1 and maps them to a witness for a corresponding L2 instance. So 11 reduction also requires a third machine to map L2 witnesses back to L1 witnesses, but we just don't require that here. Yeah, I'll also mention that to my knowledge, maybe all known NP-hardness reductions are 11 reductions. So, right, and the proof of that first statement is very straightforward. So I'll show you one direction of it right now. Okay. So let's assume that witness encryption exists for SAT, and we'll give a reduction from SAT to CGL. So given a SAT instance phi, we'll produce the following distribution E. It's an instance of CGL. What does E do? Just picks a bit B uniformly at random. It encrypts B using the given SAT instance phi. Let X be the resulting ciphertext. E just outputs X, the string X, and the label B. Okay, so it's like probably the simplest construction you could think of, just random bits along with the encryptions of those bits. So let's argue correctness. If phi is a yes instance of SAT, satisfiable by W, we need to show that E is a yes instance of CGL, meaning some small circuit is consistent with E. What's the circuit going to be? Of course, it'll just be a circuit simulating decryption with the instance phi and witness W hardwired into it. And then just from the correctness of witness encryption, we get that that circuit, given a ciphertext, always recovers the right label. This is just a note that it is indeed a half-Levin reduction. We can construct the circuit uniformly, given phi and W. Now, what if phi is a no instance of SAT? We need to show that E is a no instance of CGL. For contradiction, what if it's not a no instance of CGL? That means there's a circuit agreeing with E with probability half plus inverse polynomial. Just putting in the definition of X, what's happening is that a polysize circuit is looking at an encryption of a uniformly random bit encrypted with a no instance of SAT, and more often than not, it's telling you what the bit was. Okay, so intuitively, it's not hard to see that that's bad and that's violating the security of witness encryption. Okay, so that's it. That's the whole half of the argument. Here, I just kind of typed out the construction for the other direction. I won't go through it, but it's nothing more mysterious or more complicated. Okay, so yeah, that was kind of the first equivalence we can give, the simplest version, but we also expand on it a little bit and extend it to some other settings that might be of interest. So for example, maybe we live in a world where witness encryption exists, but it's only secure against uniform adversaries. Okay, so we also come up with a kind of NP-hardness of learning to characterize that situation. Turns out to be NP-hardness of the search version of CGL under a BPP black box half-Levin reduction. Okay, so BPP black box, it's like a special kind of non-black box reduction. It's a notion from a paper of Gutfreund and Toshma. basically, it just means in our case that the reduction is only guaranteed to work when the learner is actually a PPT algorithm. So it's a non-black box reduction, and being a search version of CGL, that means that the oracle does actually return a hypothesis explicitly to the reduction. So it's like kind of intermediate between those two types of reduction from the ABX paper that I talked about. Just to give you some hint as to like where these modifications are coming from. If you remember in the proof I showed you, we were violating security of witness encryption just by the existence of the small circuit doing too well over E. Now here that for BPP secure witness encryption, that's not gonna suffice. That's why we made these changes to just kind of enforce that the circuit violating witness encryption was actually produced uniformly by the learning algorithm. I think if I don't rush through this, I'm going to run out of time, but we can give another statement giving a kind of witness encryption to characterize a version of the minimum circuit size problem. So this is some connection to NP-hardness within meta complexity. It's like a kind of slightly generalized version of the problem. So given a truth table, is there a small circuit doing well with respect to the truth table over a given distribution? It turns out to correspond to witness encryption with security not against all poly-size adversaries, but it'll depend on the parameters of NP-hard MCSP. It'll be witness encryption where the ciphertexts only have logarithmic length. So just kind of a different regime. You also need to assume a circuit lower bound for exponential time, kind of a technical thing. I won't get into it. Yeah, but by the way, I should mention that this problem and also CGL, these problems are actually NP-hard with the right parameters. But they're NP-hard under randomized reductions, and that doesn't seem to yield any non-trivial witness encryption. I'll talk a bit more about that later. Okay, but one takeaway that you might have at this point is that if you do believe in these kind of stronger forms of cryptography, like IO and witness encryption, then you should believe that learning is NP-hard in the improper setting. Okay, and not only that, but you should believe that it's NP-hard in like this very strong sense of a deterministic many-one reduction to the decision version of the problem. And also from the sort of cryptographic regime security, you get even like the same reduction working no matter what size of hypothesis gets returned by the learner, something like that. It's NP-hard in a very strong sense. Yeah, so I just want to make the point now that there's really a long way to go between the level of NP-hardness that we actually have for learning, like in the semi-proper setting, and what NP-hardness maybe we should believe is actually true. And even between what we have and anything that would start to get us like some cryptographic consequences. Okay, so in that sort of, optimistic spirit that maybe we should be able to get stronger NP-hardness, we kind of complement our earlier statements with actually some new NP-hardness of learning. So trying to take some steps in the right direction. A little bit of background. There's a paper recently from Hirahara where he gives some NP-hardness of learning in a semi-proper setting. So his kind of main result there is concerning the concept class of programs rather than circuits. So it's kind of a non-standard concept class for PAC learning. But I think it's also implicit in the work, given the techniques there, that you can get some NP-hardness of learning circuits, but at some kind of cost to the parameters. So there seems to be some sort of trade-off. So what we can show is that actually there's no trade-off, and we can get Hirahara's NP-hardness of learning for the setting of circuits instead of programs with the same parameters. So I won't say much about the techniques here, but I'll just say that the reduction is very much the same as Hirahara's reduction. There was just sort of one missing technical piece, and we stumbled across it in a paper from Holmgren and Rothblum and realized it would solve the problem there. Okay, now we're also actually able to get some NP hardness of learning in the improper setting, but then again, we have to go back to a sort of non-standard concept class. So we show that it's NP hard to learn programs in the improper setting, but this is incomparable with Hirahara's result because here we have to look at programs getting oracle access or random access to their inputs. Okay, so it's a different concept class. The proof idea here is starting from a paper of Wang, Longo, and Ren. In that paper, they show unconditionally there exists a sort of oracle world in which witness encryption is possible, unconditionally. So given that, and given our sort of main equivalences, we know we also get some NP hardness of learning in that oracle world. And there's some sort of trick we can do of like taking those oracles, which only have polynomial length, and just including them in all of our example strings, all of the inputs to the programs. And that's what results in this sort of NP hardness. Yeah, maybe I'll mention that in their paper, in order to get security against a machine with resources of some size, you require an oracle polynomially longer than that. So that's just intuitively sort of why we have to talk about programs running in time, maybe less than the length of their inputs. All right, so we also get some consequences of NP hardness of learning for more standard forms of cryptography. So for one thing, we can improve the result from ABX that I started with. So if learning is NP hard under randomized non-adaptive reduction, that first kind of reduction, we can get all the way from worst case hardness of NP to the existence of one-way functions, excluding two of Pagliazzo's worlds. And if learning is NP hard under the second kind of reduction defined in ABX, and okay, we also sneak in that it needs to be a half-Levin reduction, that would get you all the way from worst case hardness of NP to public key encryption. Okay, so maybe some sort of interesting comparison between the two types of NP hardness. Yeah, so I'm just gonna conclude now. I think there are probably lots of directions you could try to look into, but one thing I want to mention is just that there has been a really kind of amazing amount of progress in the last few years in the study of NP hardness, like particularly problems in meta complexity, but problems about learning too. So using some really sophisticated techniques like PCP theorems and ideas from cryptography. So given that, and given our equivalences that I've been talking about, is there any hope to get some interesting forms of witness encryption unconditionally? Maybe we could hope for witness encryption secure against adversaries from restricted circuit classes, maybe even witness encryption secure against adversaries like running in just a little bit more time than the time of the encryption scheme. Something like that could be interesting. And because I have a couple more minutes, I'll also mention that so Hirahara's NP hardness of learning and our follow-up, the reduction there is actually a half-Levin reduction to CGL. Okay, so yeah, as I mentioned, unfortunately, it's a randomized reduction, and that seems to like resolve into a form of witness encryption that seems to be trivial. It's like encryption and decryption somehow have access to some shared randomness that the adversary doesn't get to know, so it's unfair. But I mean, it's true that if this reduction could be de-randomized appropriately, that would imply some kind of limited amount of witness encryption. So I'll end there.